Welcome. Thank you for joining me in case you missed class today and missed this important information. So here we have a one-day snippet just relating the ideas in chapter 3 to everything we did in second semester. Okay, so basically today is just a very quick snippet of 12. The minimum, what do you need for the AP exam from chapter 12? So, chapter 3, we reviewed a lot about scatter plots, right? Collecting data and then finding regression lines. Now, when you're finding regression lines, actually that data in the scatter plot, we can view that as a sample. Okay, view that as a sample of data. And what that means is that the slope we calculate is actually a sample statistic. So if we view our slope as a sample statistic, we can actually use inference procedures on it. We can make a confidence interval to see the true slope of the entire population. We can run a hypothesis test comparing the slope to 0 to determine if there actually is a slope at all. So let's relate these ideas to everything we did second semester. So remember, in the formula packet, we talked about a confidence interval is a statistic itself. So in this case, our slope, which I'm going to use B to represent, our slope plus or minus the critical value, which in this case is a T, specifically with degrees of freedom of the sample size minus 2. Now, that's a little bit hard to remember. Is the only time you've ever seen this. The way I think of it is because a scatter plot has two directions, x and y. Because of those two dimensions, those two variables, we're going to take 2 away from the sample size for the degree of freedom, okay? And then, of course, our standard deviation, or in this case, we call it standard error of the slope. And that is another thing in our Minitab output that I'm about to show you today, okay? So, putting those things together, and we get some really easy, fun things that we get to do today. So let's dive right in just so I can show you what my expectation will be, what shows up at least once a year on the AP exam. Scientists have long believed that linear regression could be used to predict the brain weight of non-human mammals from the body weight. In one study, body weight in kilograms and brain weight in grams of 22 non-human mammals were measured. A linear regression analysis was performed, yielding the output below. And they want us to assume all conditions are met, so which of the following expressions represents a 95% confidence interval? So again, we just talked about at the center of the confidence interval is the sample statistic. So here at the center of this one is going to be the slope. We're inferring about slope. Well, that's why we took some time to review this first, because slope is right in line with the variable. So here our slope is going to be the 1.096. Plus or minus our critical value. So remember, critical values we find in table D. These ones specifically, when we look at the degree of freedom, so here n being 22 means we're going to have a degree of freedom of 20. Okay, so look, 25% confidence, 20 degrees of freedom, I'm getting 2.086 as my critical value. And then that standard deviation will again just follow in line, and there it is, 0.1308. So honestly, I think that the stuff we get to cover today, I really like the stuff we get to cover today because that's mainly the gist of it. Here, that pretty quickly gives you the answer of A, as long as you remember how to find that critical value, okay? Let's do another one, shall we? So a statistic teacher wants to determine whether there's a linear relationship between high school students' heights in inches and the lengths of their feet in centimeters. The teacher obtains height and foot length measurements for a random sample of 23 students at the high school and generates the following graph and computer output. Provided the assumptions for inference are satisfied, which of the following provides a 95% confidence interval estimate for the slope of the population regression line for predicting foot length from height? So again, we're doing a confidence interval around slope. So here's my variable which means here's my slope. So 0.583 plus or minus the critical value. Well, here they tell us there were 23 students, so our degree of freedom would be 21 this time. So 95% confidence, 21 degrees of freedom, I'm getting 2.080. Then just follow the line to the standard error, 0.138. All right. So again, I really like this stuff that we get to do today. That gives us answer B. Because again, now that you know how to do this, you've been doing this for a long time, this just inherently makes sense how to make this. Our next one, as part of a class project at a large university, Amber selects a random sample of 12 students in her major field of study. All students in the sample were asked to report the number of hours they spent studying for the final exam and their score on the final exam. A regression analysis on the data produced the following partial computer output. Amber wants to compute the 95% confidence interval for the slope of the least squares regression line in the population of all students in her major field of study. Assuming the conditions for inference are satisfied, which of the following gives a margin of error for her confidence interval? Okay, so this time we're talking about margin of error. So margin of error, remember, that's just the critical value times the standard deviation, right? So here we actually only need two things, just critical value and standard deviation. Well, 95% confidence, if we have 12 people, that means, that means our degree of freedom is 10. So let's look that up, 95% confidence, 10 degrees of freedom. I'm getting 2.228. Then of course, here's our variable, which means here's our slope, which means here is our standard deviation. So standard deviation, 0.745, and that's going to give us our answer of A. So again, I really like all of these ideas that we're seeing today, okay? Now, let's talk about a little bit more of the interpreting piece about what this interval is actually giving us. Well, a slope of 0 would represent having no correlation between our two variables, right? So a slope of 0 basically means that the explanatory variable isn't impacting the response variable at all. So if 0 is in the interval, it's possible there's no association between the variables. But if 0 is not in the interval, then there's evidence that there is a correlation between them, an association between them. So a 90% confidence interval for the slope of a regression line is determined to be negative 0.181 up to 1.529. Which of the following statements is true? All right, so this one takes a little bit to wrap our minds around. Now what I notice, two of the questions reference the slope of the sample regression line, okay? So our regression line, what was our actual sample slope? Well, in a confidence interval, isn't the sample dead center? So if I wanted to calculate the slope of our sample regression line, again, I could just average the two numbers there. The middle of my interval would provide me the sample slope, okay? And if you notice when I average that, I don't get either one of those, okay? So neither D or E are correct. Again, that is not what the center of our interval is telling us. C, a scatter plot of data would show a linear pattern. So this one, it sounds super tempting. It sounds good, because why would you perform inference on slope if it's not linear? But again, we talked about this in chapter 3, the idea that unless you're looking at the scatter plot and see a linear pattern, or unless you're looking at the residuals and see no pattern, you can't make this statement just because people decide to start making linear regression lines and stuff like that. You have to actually see the data or see the residuals, the residual plot, to make a determination like that. B, the sum of the residuals for the data based on the regression line is positive. This is something we didn't touch too much on, but back in the chapter we did have the conversation that the sum of residuals, the reason when we make the least squares regression line, the reason we square it, the residuals would actually always add to 0. The residuals always perfectly balance each other out unless you square them. So B is not right. So that leaves A. The correlation coefficient of the data is positive. Okay, well, of the data means of our sample line, right? Well, notice our sample line, didn't we already talk about our sample line has a slope of 0.674? And remember, correlation matches the sign of the slope. So our sample slope is positive, so the sample's correlation coefficient would also, therefore, be positive. All right. So next let's talk about hypothesis testing. So again, similar to 11 or to 10 and 11, we're going to be having our null be that there's no correlation. Alternatively, that there is. No correlation, no association would be that it equals 0. Then obviously the alternative would be a direction to that. Do you think it's negative, positive, or not equal to? Meaning you just think there is a relationship, you just don't know which one. So the test statistic itself kind of follows the idea of the packet. So our statistic minus the parameter divided by standard deviation. So again, standard deviation is easy. That's just standard deviation of the slope. Our statistic is going to be our sample slope minus a parameter. Well, most often, in fact, every time I've ever seen this pop up, we're testing against 0. Okay, so to make this even a little bit easier, it's literally just your sample slope divided by your error of the slope. Okay, so let me show you again how that can play out. So here, a research study indicated a negative linear relationship between two variables, number of hours per week spent exercising and number of seconds it takes to run one lap around a track. Computer output from the study is shown below. Assuming all conditions for inference are met, which of the following is an appropriate test statistic for testing the null hypothesis that the slope of the regression line is 0? All right, so again, following our pattern of making a test statistic, it says take your sample statistic. Well, our sample slope is taking that variable and it's right next to it. So negative 2.20 minus the parameter. Well, aren't they saying to minus 0? So really, we don't even have to worry about that minusing 0 part because, again, it doesn't do anything. Over the standard error of the slope. Well, again, if you just keep going, it's right there. Okay, again, giving us an answer of D. All right, so I apologize, my screen isn't letting me actually move down. So, but really quickly, let's just talk about, now that we've briefly covered how this can pop up in multiple choice, let's briefly talk about how this could also pop up in terms of FRQs. Now, in and of itself, Chapter 12 doesn't very often pop up as an FRQ, okay? And if it does, it will say, assume all conditions are met, which is why I'm not even covering what the conditions are, because there's 5 of them, and they're awful. But usually, sometimes these ideas can be embedded within Chapter 3 FRQs. So that's why we spent so much time covering 3 first, is so you remember all those concepts, so these ones make more sense. So I have 2 FRQs here that I would like to discuss with you And then, of course, you have the opportunity to finish the rest of the packet off to practice. So, windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amperes for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity production based on wind velocity is given below. The regression model assumptions were checked and determined to be reasonable over the interval of wind speeds represented in the data. Which were from 10 miles per hour to 40 miles per hour. So again, this is the thing that I talked about. The assumptions were checked and determined to be reasonable. So that means you don't have to worry about them yourself, which is good because, again, there's so many of them that it's not worth trying to make you memorize at this stage of the game. So let's talk about use the computer output above to determine the equation of least squares regression line. Identify all variables in the equation. All right, so we want to make a least squares regression line. So here, this wind velocity then must be our x, and they are talking about the relationship between that velocity and electricity production. So obviously, according to that, our y is going to be the electricity. So we're going to be predicting electricity. The constant, that represents our y-intercept. Constant means the number by itself. The wind velocity, what's connected to that, is obviously our slope then. And remember, if you use words as you're forming your equation, then you don't have to worry about labeling them separately, okay? Part B, how much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day where the wind velocity is 15 miles per hour? All right, so for this, how much more? So I'm going to do my work down here just because there isn't space the way that I've written it. So how much more? That's the idea is if I plug in 25 and I plug in 15, that phrase how much more means I'm looking for the difference in the electricity production, right? So if I plug in 15.137 plus 0.240 times 15, if I plug that into my calculator, 0.135 plus 0.240 times 15, 3.737, and I plug in 25, 6.137. Again, what I'm looking for is the difference between those. That gives me 2.4. And then the unit, I believe they said, is in amperes. So again, that one is just recognizing, finding out how much more. Well, again, all we're doing is we're talking about finding each one and then finding the difference between the electricity production. What proportion of the variation in electricity production is explained by the linear relationship? Percent variation, proportion of variation. Well, that sounds a lot like R squared. Okay, so that one is honestly just asking you for R squared. And again, the nice thing is R squared is something they provide in the table. Okay, 0.873. So that means 87, we would expect 87.3% of the variation to be able to be explained by this linear regression model that we just made. Is there statistically convincing evidence that electricity production by windmill is related to wind velocity? All right, and they want us to explain. So here, statistical evidence. So this is essentially asking us for a hypothesis test, okay? So again, here, the hypothesis test, if we think of it as such, hypothesis test would be a t-test for slope, right? So, and how to know what's t? Well, because we did reference before that this thing has a degree of freedom. We have been referencing this as a t-test. So this is basically a t-test for slope. Plan. They told us that we could assume everything had been met, so we also don't have to worry about that part. I'm sorry, in the state, I'm sorry. And maybe I should reference the null is that the slope, the actual slope is 0. Here, we're not given a direction, so we'd be testing that the slope is not 0. I'm sorry, I should give you that as well. But again, I think that is kind of a natural consequence of hypothesis testing. We didn't mention that right above. Now, in the do step, well, let me show you two cool things. Notice if you keep following slope to the actual slope, to the standard error of the slope, notice these two things, T and P. So those are the two things we need. Those are the test statistic, right? And the p-value. So all of that is actually provided in the table. And I'm sorry, I forgot what that value is already. Is 12.63. P-value is basically 0. So is there evidence? I would say yes. So in our conclusion, because our p-value is so small, we do reject the null. In rejecting the null, it does mean that there's evidence that electricity production by the windmill is related to wind velocity. I'm not going to write all that down, but I'm going to repeat it one more time for you so you can write it down. So again, because our p-value is so small, less than 0.05, we reject the null. By rejecting the null, it means we do have evidence that electricity production by a windmill is related to wind velocity. So again, that would be just kind of the shell of what you would have to do if this happens to pop up, which again isn't actually that hard, I don't think. Again, you know slate plan do conclude. The only thing is this time it gives you everything inside the table. You don't even have a calculator command for this. Okay, you just have to know how to pick out the right information. So let's do one more, and then we will call this a day. A manufacturer of dish detergent believes that the height of soap suds in the dish pan depends on the amount of detergent used. A study of the suds heights for new dish detergent was conducted. 7 pans of water were prepared. All pans were of the same size and type and contained the same amount of water. The temperature of the water was the same for each pan. The amount of dish detergent was assigned at random to each pan, so the amount of detergent was added to the pan. Then the water in the dish pan was agitated for a set amount of time, and the height of the resulting suds was measured. A plot of the data and the computer output from the least squares regression line to the sample data are shown below. Write the equation of the fitted regression line. All right, so here again, we've already done this part, right? We already know how to do this. So here we're talking about the amount and then the height, right? The height that it gets. So we're predicting height, again, because this is always your x. Across from the constant is my y-intercept. Constant means the number by itself, plus the slope. The slope is what's across from the variable. All right, so we have that. So now part B. Note that S equals 1.99821 in the computer output. Interpret this value in the context of the study. All right, so that S. All right, so that S is the standard error or standard deviation of the residuals. Okay, so standard deviation of residuals. So remember we talked about don't get bogged down on exact language here. Okay, all I'm going for is that you have an understanding of what this is. Standard deviation of the residuals is basically the variation, right? So it is the average variation oh, the 1.99821 measures the average variation in the actual heights of the suds to the regression line. Okay, so again, the residual means the error in from the line to the point, so the standard deviation of that would be the average variation that we're seeing. So the average variation in the actual heights compared to the regression line itself. Okay, so again, as long as you get the general idea, you would be fine. Okay, don't get bogged down with exact language. Just understand the idea. Standard deviation is always very average variation. In this case, from the actual point to the actual height to the line itself. Now, identify and interpret the standard error of the slope. Okay, so standard error of the slope. Now I'm going to have to erase this. I apologize. Standard error of the slope. Well, again, we know here's the slope, so here's the standard error of the slope. So again, hopefully you know by now that it's the 0.7553, right? Just in a line from the slope itself. Now, what does it mean? Now, we've talked about standard error before. Okay, so standard error of the slope or of the proportions of the means. So whenever we're doing statistical inferencing and sampling, basically now that standard error is the idea of taking many samples. Is the average variation of it from the true thing, okay? So what it means, so the standard error of the slope is 0.7553, and it measures in repeated sampling the average variation of a sample slope to the true slope. Okay, just like when we did it for proportions, it was, hey, in repeated sampling, it's the average variation of our sample proportion to the true one, or same thing for mean. So it's that same general idea each time, this time now just in context of slopes. All right, and that is actually it for our notes today. Okay, so again, thank you for watching. I really do appreciate it because I do want to make sure you get this material before the AP exam. So, and just like with the other packets that we're doing, make sure now you take time to do the practice problems on them as well.